Hi, in this video we are going to talk about the running time analysis for the heap data structure. So what about the memory complexity? We have n items we want to store in a heap data structure, so we have to allocate memory for an array with size n. That's why the memory complexity is going to be linear in the sense that it's going to be ordo n. Of course, it's not that counterintuitive because somehow we have to store these n items. Okay, so it's going to have ordo n memory complexity. What about other features of the heap data structure? What about finding the minimum or the maximum item? It's going to take ordo 1 constant time complexity, so it is extremely fast. Yeah, this is why heaps have came to be, in order to be able to find the minimum or the maximum in order 1 constant time complexity. So because in the heap the highest priority item is at the root node, it is quite easy to achieve this running time. We just have to get the 0 index from the heap array, and it's going to be the item we are looking for. For a maximum heap, it's going to be the maximum item. For a minimum heap, it's going to be the minimum item. What about inserting new items? We can insert at the next available place in the one-dimensional array, so basically we just have to append it at the end of the one-dimensional array, so increment the array index and insert it there. It's very fast, ordo 1. But it's very important that on every insertion we have to make sure that the heap properties are met. What are the heap properties? This is what we have been discussing in one of the first lectures, that for example the tree-like structure has to be complete. Then, for a maximum heap, the parent has to be greater than the children. For a minimum heap, the parent should be smaller than the children. So it may take ordo log n time to make sure that the tree-like structure is a valid heap data structure. You may pose the question that, okay, we have been discussing this logarithmic time complexity. First of all, it's important to know that it is the base 2 logarithm. And why? Because a node has at most log base 2 n parents, so at most log base 2 n swaps are needed. So whenever we come to the conclusion that the heap is not valid and we have to make some reconstructions and swap operations, then we are sure that there's going to be at most log n swap operations. And that's why we are able to say that in the worst case, insertion is going to take ordo log n. What about removing an item? We usually remove the root node, so removing the root node is quite fast. We just have to delete it in ordo 1 constant time complexity. But of course we have to make sure that we met the heap properties. We have to replace the deleted node, so we are going to replace it with a leaf node as we have been discussing in one of the previous lectures, and then we have to check whether the heap properties are met. And it's going to take logarithmic time complexity again in order to reconstruct the heap. So basically finding the minimum and the maximum is going to have ordo 1 constant time complexity, and the insertion and the remove operation is going to have logarithmic time complexity. It's quite easy, and you may pose the question that what's the difference between heaps and binary search trees or AVL trees. The main difference is that the find minimum or maximum. For a binary search tree, the maximum item is the rightmost item, the minimum item is the leftmost item. So finding the minimum for a balanced tree is going to have logarithmic time complexity, and we would like to make better. That's why heaps have came to be with ordo 1 constant time complexity, because sometimes for optimization problems, shortest path problems, or minimum spanning tree algorithms, we would like to get the minimum or the maximum value in constant time complexity very fast. And basically that's what I have been talking about in one of the previous videos, that this is how we are able to boost some algorithms with the help of data structures. For example, finding the shortest path in a graph. We are able to reduce the running time with the appropriate underlying data structure, for example heaps, and because we are able to find the maximum and the minimum in ordo 1 constant time complexity. This is why data structures are extremely important. We are able to boost our algorithm with the help of data structures. So that's all about the running times for Heap. Thanks for watching.